Hello everyone, this is Riti Chaudhary from the School of Computing Science and Engineering, and in this course we will read about cyber security, and the course code of this subject is BSCS 2380. So the very first concern about cyber security is, what is cyber security? Cyber means information, and there are many kind of informations available around the world, amongst which some of the data or information are very crucial and they must be protected, like the information of our bank account, that is finance and money transactions, and then the defense, those informations that are used in defense, and also the some information that are used by the government. So all these informations were very much needed to be protected from the ancient time, but as the invention of digital devices occurred, as well as the internet plays in significant role in today's world, these informations are needed to protect it. There are many types of attacks that are available in online as well as in offline. So we need to protect our data in a manner so that any kind of unauthorized access can be stopped. So before going to the detail of different cybersecurity algorithm, we first need to know about some basic mathematics. So we will go through the finite fields and number theory that will be concerning with modular arithmetic Euclidean algorithm, likewise. So the first thing is group. What do you mean by group? Group concerns to the discrete mathematics. So it is basically a set and the operation that can be operated on this set. And if the set is consisting of certain elements, let's say a comma b, c and d, and so on, then for each and every pair of elements, that may be a b, that may be a c, or b c or c d, certain properties are there which must be hold. What are these properties? That the first property is called, this is a1, that is closure. Closure property says that a and b or c or d, whatever elements are there in G, must belong to G, then the operation also belongs to G. What would be the example of that? Suppose we are having 2, 3, 6, 7 and 9. This is the set. Now take, if we'll take these two elements, then you will find, suppose we are giving the operator as dot product, then what we will find, that 2 cross 3, 2 dot 3 is equals to 6, and 6 belongs to this set. So that means there is a possibility that 2 and 3 is closer within G. But you will find out that if we'll take, we will consider two elements as 3 and 6, this element and this element. Then if we'll use the dot product, then the result will be 18, and 18 is not in G. So that means 3 and 6 is not closer within G. So this is the first property. The second property is associativity. Now what is associativity? That if we are having three elements like 8, 2, 3 and 6, then this property must be whole. So let's check whether this is possible if we'll take a dot or not. So if we'll take, suppose 2 dot 3 dot 6 is equals to what? 6 dot 6 is equals to 36. Now we can write it as 2 dot 3 dot 6, because 3 dot 6 is equals to 18, and it will multiply with 2, it will give 36. So in this way we can check the associativity. Now there must be an identity element within G. Let's suppose the element is such that A dot E is equals to E dot A is equals to A. That means if we'll multiply with the identity element, we will have the same element back. So suppose 2 is there and we are multiplying with 1, then we will get 2. You can multiply any element with 1, you will get 1 back. So that means identity element will be 1 in case of the multiplication as an operator. Now A4 is another element, that is the inverse element that must be in G. And what do you mean by inverse element? That if we'll have an element, we'll multiply with the element, let's say A, and we will get 1. That means what? A dash will be 1 by 2. So now see, if we'll have A dash, we can write 2 into 1 by 2, and that will give us 1. So that means that we are having one inverse element. So inverse of 2 is 1 by 2. So we will have the inverse such that A dot A complement will be equals to A complement dot A is equals to E. So in this way we can check whether a set is group or not. Now abelian group, if the group is commutative, that is for any element in G, A dot B is equals to B dot A, then we can say that the group is abelian group. So similarly we can check that if 2.3 is equals to 3.2 or not. Yes, it is closed under multiplication. So we can say that this is the abelian group if this condition A5 holds. Now the cyclic group. Cyclic group is a kind of group where we will have one element in the group. From taking the one element and its power, we can generate all other elements within the group. Suppose what would be the elements in the group? That A to the power 0, that will be identity E. Like in case of something to the power 0, 5 to the power 0, we write 1. So 1 is the identity. Now from that we can generate all the other elements, like A to the power 1 will be one element, A to the power 2 will be, A to the power 3. We can generate the elements using A's power. So if we found this kind of set, then we can say it's a cyclic group, and A is called the generator of that cyclic group. So here we can see that this is the distributive law as well as the and this is the associativity law, which is A dot BC is equals to AB dot C, as we have seen in the previous slide. And distributed law is consisting of both the operations as plus as well as here it will be a dot. So we can have this kind of property in the case of distributed law. This is also another property. This must be hold within the set. Then we can say this is a ring. And if it is commutative, like if we for any element the multiplication holds, like A dot B is equals to B dot A, then we can say that this is a commutative. Now here in this slide we can see there is a set which is called field, and field is also being operated into two operators using plus and multiplication, which holds all the properties from A1 to M6 and then M7. So you can see and there I have here I have shown it in a diagram where all the properties of groups are mentioned up to this. Then if it is a group and it is commutative, it will be the abelian group. If it is a abelian group and it is having the properties closure under multiplication, associativity of multiplication and distributed law, then it will be a ring. Then for commutative ring, there must be two elements such that A dot B is equals to B dot A, and dot is the represents the multiplication here. Now you can see that integral domain, this is there must be uh, all the elements which are not having any device as a 0. So that is called integral domain. And if an integral domain follows the rules of multiplication inverse, then we can say it is a field. And what does the multiplicative inverse say? That if you are having A as an element and A inverse as multiplicative inverse, then you can say that A inverse is equals to A inverse dot A is equals to 1, and this operation must be multiplication. It cannot be any other operator as plus or minus. So now the finite field, that is called the Galois. So we can say a finite field as Galois of order p, where p is a prime number and all the elements must be within Z that is the set of integers. This is the generalized notation for showing the set of integers. And suppose n or p, whatever you can find, is a prime, then all of the non-zero integers of Zn are relatively prime to n. So whatever set the finite fields will contain, all the sets, all the n will be relatively prime, and therefore there exists a multiplicative inverse for all the non-zero integers in Zn. So it will also have the multiplicative inverse, and we can find out the multiplicative inverse using this formula: W cross Z is congruent of 1 mod P. So we will come back to this portion with some mathematical implementation as well as some algorithms. Okay, thank you very much for today's class. I hope you have enjoyed it. Thank you.